And good evening, everybody. The weird world of the very, very small. I think this might be the first time I've given this particular talk to an astronomical society, because not surprisingly, most of the time, astro societies are more interested in the large scale universe rather than what's going on the very small scale. So maybe this will be a little different to other talks that you've heard about. So I'm going to start with giving you a little bit about sense of scale, starting from the everyday scale that we're used to and going down to the scale where we're talking about the very, very small, being something of order nanometers. Nanometers being 1,000th of a micron is 1,000th of a millimeter. So a nanometer is 1/10000000th of a meter, and that's the sort of scale that we'll be talking about. I'll be having a quick detour through a sense of symmetry to give us an idea of how we know what the world is made of on a small scale, and think about how that tells us about underlying structure of matter, what we're made of effectively. And then we'll be looking at the quantum world, and we'll finish by how we can actually use the quantum world to actually see atoms themselves. So I guess we're all familiar with the scales of, well, certainly meters and above. Our own natural scale is of order meters. I think we're all comfortable with kilometers and thousands of kilometers. We start to go a bit weak at the knees when we try and imagine light years and billions of light years, but we're generally comfortable with meters down to about millimeters or so. That's, roughly speaking, one of the smallest objects you can see would be just a fraction of a millimeter. If we go down in size a little bit further, this object is about 1/20th of a millimeter, or about 50 microns in diameter. Perhaps you recognize it. It's a pollen grain. And if we go to not the natural world, but if we go to the manufactured world, the man-made world, we can actually manufacture mechanical devices at the scales of microns and above. This cog and ratchet mechanism is of order 10s to 100 or so nanometers, microns in diameter. But of course, mechanically, we can go down to a particular size, but if we want to go to very small sizes, we're not limited by mechanics, because we can move to electronics, and there, as I'm sure you know, we can go down to much smaller scales. For instance, a microprocessor chip that's probably in the computer or iPad or phone, whatever it is you're using to watch this particular talk. Microprocessors will have areas from square millimeters up to square centimeters, and they may contain 10 million, probably more like 100 million or even a billion transistors. So the size of individual components in electronic circuits are getting comparable to nanometers. We're not quite there yet, but certainly we have objects that are only tens of nanometers in size in a typical microprocessor. So we can certainly get down to the nanoscale, and that's one of the reasons that understanding the weird world of the very, very small, it's important, because it does directly affect how, for instance, computers work. It is not just something fanciful that we can think up, it does actually impact on reality, it impacts on technology. So let's just think about the structure within. What is the world made of? In other words, if we pick up a rock and look at it, what do we think is actually inside that rock? How can we tell what the world is made of? What sort of clues do we have? If we want to know what is the building blocks of matter, then what sort of clues do we have? Well, if we go back far enough, we find that Aristotle tells us that, well, everything is made of fire, air, earth, and water. A nice simple periodic table, if you like, with just 4 components. That's nice and simple, but it doesn't really explain the complexity of everything we see around us. Galileo had a rather more pragmatic attitude, and that is that the nature of the world around us should be determined by quantitative experiments, actually measure things, rather than by qualitative intellectual arguments. In other words, instead of saying what should happen if we do this, you should ask what actually happens, rather than say what do we think ought to happen when we let go of an apple. Should it go up? Should it go down? Let's actually make a measurement and see what actually happens. So if you like, Galileo was arguably the first experimental physicist who actually relied on making measurements of the real world rather than simply philosophizing on what might be. This, of course, culminated some years later with Newton, who developed laws of motion, laws of gravity, the universal law of gravity, and did experiments that told us about the nature of light. And bundled together, that effectively is what we now call classical mechanics, to distinguish it from, if you like, modern physics, which is a bit of a misnomer, but modern physics refers to everything in the last century or so, which has, in a sense, overturned everything we thought we knew from Isaac Newton. But it still stands as a tour de force in that one man almost single-handedly laid down the groundwork for the laws of motion, the laws of gravity, and the nature of light. So as of the 1600s, we may think that, well, the universe appears to be clockwork. You wind it up, let it go, and then everything, whether it be a billiard ball moving across a table or whether it be Jupiter going around the sun, everything is just then dictated by the laws of physics, Newton's laws of motion. If you push on something, it'll move in a particular way given by Newton's laws. And if you know where everything is now and which way it's moving, then you can predict where it's going to be in 5 minutes' time, 5 years' time, or 5,000 years' time. As long as you know where everything is and how everything is moving, you can predict the future, because the future is based on clockwork. And once the mechanism is set up and running, then you just watch the mechanism and you can predict the future. So it's nice to think of a clockwork universe because it's nice and comfortable. Everybody can get their head around what's going on in such a universe. But if we want to know what's inside matter, we look at snowflakes, for instance, and what do we see? Well, we see lots of different structure, but we see patterns, we see symmetry, we see a six-fold symmetry in a snowflake, and that makes us think, well, if we want to understand what's going on inside, surely that six-fold symmetry must be important. If billions upon billions of snowflakes have been made, all different shapes, but all six-fold symmetry, surely that must be important. And we can apply the same argument to effectively anything we pick up, whether it be a rock or a piece of metal. This particular metal here seems to have a very odd shape to it. This particular metal happens to be bismuth. I assume it's bismuth based on the word in the background there. And so that must tell us something about the building blocks of bismuth, that they must fit together in a particular way so as to make crystals that look like this on the macroscopic scale that we can see. And similarly, if we look at other crystals, we say, well, this crystal appears to want to be a sort of cubic or cuboid type shape. So whatever the building blocks of matter are, they must fit together in a particular way, in a particular pattern that gives us these particular crystals. And more recently, this wasn't known to the ancients. This is a relatively new discovery. Some crystals want to be not cubes or hexagons, but some crystals want to be dodecagons or dodecahedrons. Why would that be? What does that tell us about the building blocks of this material that form this particular shaped crystal? When we look at the macroscopic shape and symmetry of crystals, surely that must be telling us something about the underlying structure. And that was the argument that led through a number of centuries to the argument about what these building blocks must be and how they fit together. I'm not going to turn this into a history lesson, but just to give us an idea, you can argue that it started with Democritus here, who said that if you take a piece of material and cut it in half and cut it in half again, you can't keep cutting it in half. Eventually you get down to something which is indivisible, the building blocks of matter. They were called atoms at the time, and that word, of course, has stayed with us. But the nature of what an atom is has been a matter of debate for many, many centuries. Here are some of the key players over 300 years, from 1600 to 1900. I'll give you just a second to look at those faces. I'll be asking questions later. Do you recognize the faces of these particular individuals who had key roles to play? Well, let's just go through some of the names here. There's Boyle. We've already had a look at Newton, and then we have Lavoisier, and then we have Dalton, and then Avogadro, and then Maxwell, and then Boltzmann. Perhaps you know the names, perhaps you know some of the faces. Sometimes you don't always put a name to a face. So I'm not going to go through the roles of each of these individuals, but all of them had some role to play in asking the question, how is the universe put together, and what are the fundamental building blocks of matter that allow us to build essentially rocks and you and me and mountains like the one behind me? What are they all made of? If we think about what happened in the 1800s, I'm just going to pick out two particular events in the 1800s that relate to our understanding of the nature of matter and the nature of light. So in the early 1800s, we've got Young, who was thinking about the nature of light. It was arguable as to whether light was a whole load of corpuscles, or particles if you prefer, or whether light had a wave type nature. And Young performed an experiment in which light was passed through two slits, and he found interference, just like you would expect in water waves. And so he determined back in early 1800s that light, regardless of which particular electromagnetic wave we're talking about, just thinking about visible light, light is a wave. And later on in the same century, J.J. Thomson was looking at cathode rays, and again, it was not clear at the time whether these ghostly rays that could be seen inside vacuum tubes, whether they were waves, just like light, or whether they were corpuscular, whether they were particles. J.J. Thomson determined that the elements of a cathode ray were negatively charged particles, and we now call these particles electrons. So it looks like matter is made of negatively charged electrons and presumably something else. It was understood that matter is not charged, so if part of matter is negatively charged electrons, there must be something else that we're missing, which is positively charged, and it wasn't known exactly what that was. And there were various models of what the building blocks of what we now call atoms must be to explain why we have negatively charged electrons and something else which is positively charged. And so it looked like things weren't too bad leading up to 1900. We've got an idea of atoms. We now know that one of the components of atoms, electrons, and we know that light is a wave and electrons are particles. However, everything after 1900 changed completely. And I'm not even going to show the whole century here, because effectively all of the turmoil in the 1900s happened in these first 3 decades, from 1900-ish to about 1930 or so. Again, here are some of the key players. If you just cast your eyes over these faces, some of them will be recognizable to you, I would imagine, some of them perhaps not. So let's have a look at who these people are. Becquerel, Planck, Rutherford, everybody recognizes Einstein, I'm sure, Niels Bohr, de Broglie, and then we have the architects of quantum mechanics, Heisenberg and Schrödinger. From here on, I will use QM in the slides as an abbreviation for quantum mechanics. So what was going on during these 3 decades? Well, there were quite a few key observations, key measurements, key experiments. Each of them I'm going to show on the timeline on the bottom. I'm not claiming that each of these was necessarily attributed to the person whose photo sits directly above them. But key observations were radioactivity, particles sent out from atoms, that light is a particle. We have a concept of an atom with a nucleus, thanks to Rutherford. We now have an idea that probability plays a key role, and de Broglie showed that electrons are waves. And here on the right, again, I've just labeled it as QM because here we have the key architects of quantum mechanics. So notice that one of the key things that happened during these first 3 decades was that we've completely overturned what we said in the previous slide. In the previous slide, we were all comfortable with the fact that light was a wave, but now it looks like light is a particle. And again, electrons we were fairly sure were particles, but now it looks like electrons are waves. And that's why the previous slide was labeled wave-particle duality, because we have this fundamental difficulty in deciding whether anything, regardless of whether we thought of it as a particle or thought of it as a wave, it's rather tricky to pin these things down. It seems fairly fundamental. Surely it's one or the other. But no, it looks like actually the more experiments you do, the more confusing it gets. Sometimes when you measure light, it behaves like a wave, and sometimes it behaves like a particle. When you look at electrons, sometimes they behave as a wave, sometimes they behave as a particle. And the other key observation in this particular period of these first 3 decades is the fact that probability plays a key role. Unlike Newtonian mechanics, in which everything is clockwork, once you understand how the clock works, once you understand the mechanism, then once you know that these particles or these planets are in motion, you can calculate exactly how they're going to move and where they're going to be in a second or a year or 1,000 years into the future. But here we now have measurements that are being made that indicate that probability is key. We can't predict exactly how the future is going to unfold. All we can talk about is the probability of this taking place or the probability of that taking place. All of this confusion, what is the role of probability, and why can't we pin down whether particles are, as we would expect, solid particles that we can think of as particles, but sometimes have wave-like properties? And why is it that light, which we thought of as a wave, seems to have particle properties? Well, all of that confusion was brought to a head by the construction of quantum mechanics in about 1930 or so, give or take a few years, in which Heisenberg and Schrödinger effectively tried to bring together all of these disparate threads and say, here is a mathematical theory, here's a mathematical model, if you like, a construct, which allows us to describe the way reality is, the way the world works when we're talking about atoms and molecules and anything on that sort of scale. It was a tour de force, and it wasn't readily accepted simply because it came up with arguments and predictions that were very difficult to swallow. And we'll see some of those in due course in a few slides' time. But I'm not going to go through the roles of each of these individuals to how they brought these together. I'm simply going to concentrate on the main protagonists in terms of the people that we're describing. What is the structure of an atom? How is it put together? And how do atoms behave? Because these are the fundamental building blocks of essentially all matter as far as we can tell. So we tend to think of this as a sort of picture of an atom. This is how I think all of us think of atoms, regardless of whether we're the man in the street or a student or a veteran scientist. We still tend to think of an atom as being a nucleus. It just happens to be positively charged, as determined by Rutherford, and it seems to have a whole load of negatively charged electrons buzzing around it. And so regardless of whether we think that model is right or not, that tends to be the way we visualize atoms. One of the reasons that's not a very good picture is because it doesn't tell us that all of these electrons actually have different energies. When you look at all of these electrons buzzing around there, they all seem to be buzzing around the nucleus in the same way, so presumably they all have exactly the same properties. But we know from measurement that electrons in atoms have different properties, including different energies. And so a better way of thinking about electrons in atoms is to think of it a little more like this picture at the top here, where we have electrons buzzing around the nucleus, not in all directions necessarily, but in what appears to be very regulated orbits. There appear to be a couple of electrons in that inner orbit, and then what have we got there? 8 electrons in the next one, and then a number in the next one, etc. So it's not very convincing as a model in the sense that atoms are not flat, but that particular representation at least shows us that various families of electrons have different energies. Perhaps it would actually be better to think not in terms of orbits in the sense of planets around the sun, but more like this bottom idea of shells. And we've taken the shell and chopped it in half just so you can see inside. It's like a load of Russian dolls where we have an inner shell with a number of electrons and then a shell outside that, and then another shell, and then another shell. And because these electrons are all at different distances from the nucleus, they all have different energies. And by looking at how those electrons have different energies, then we can start to explain, that's why this atom reacts with that atom. We can start to explain chemistry as soon as we have a model in which the electrons have a particular structure within the atom. So one of the key roles of quantum mechanics in those days was to apply it to atoms and explain what we see when we think about atoms making up all material. In other words, we already knew that there was a periodicity in the properties of elements. Mendeleev had taken as many elements as he knew and tried to arrange them in families according to particular properties. So for instance, reactive metals on the left-hand side, inert gases on the right-hand side, for instance. These elements here all appear to be magnetic. So by arranging them in a particular grid pattern, it started to become clear that there were particular patterns of properties of elements. And as soon as we had the idea that quantum mechanics tells us that electrons should have particular, what we now call shell structure around the nucleus, then we can start to explain why we get particular periodic properties within the periodic table. And we can then start, of course, to fill in the gaps and understand why this particular element has these particular properties and why, in a chemical sense, this element reacts with that element, because we can start to understand what the electrons are actually doing. So does that mean an atom is a solar system? Does that mean the positive nucleus acts just like the sun and all of the electrons are going around it in some sort of orbits? We know that in the solar system, one planet occupies one orbit, with the exception of a few satellites and a few other objects. And we've just seen that the atom is a little bit different because two electrons or many electrons can be apparently in the same orbit. But is that a good model? Is it fine to say, well, electrons are like satellites, so we can think of a picture of an atom on the left as being a nucleus with a load of electrons at different distances in these shells? Is that just like GPS satellites going around the Earth in different orbits? Well, that is a rather confusing way of thinking about atoms because it doesn't encapsulate the real essence of the way things behave when they're on these very small scales. So although it's tempting to visualize atoms in terms of satellites buzzing around the Earth or the Earth buzzing around the sun, it is not very useful when it comes to actually understanding the properties of atoms and how they behave. The main reason why is because of this joker in the pack, which is probability matters. We can never say an electron is here in this particular orbit, and in a little bit of time that electron will be there, and then a little bit later that electron will be here, and we can trace out its orbit, just like in principle we can trace out the orbit of the Earth around the sun. Probability matters. So you could argue that it's better to think of electrons not as objects that are orbiting the Earth or the Earth orbiting the sun. It's better to think of a cloud in the sense that we can only talk about the probability of finding the electron in a particular place. These are 8 examples of how we might define where an electron is. In each case, the center of these clouds is where the nucleus is, and these clouds are representing where are we likely to find the electron if the electron has a particular energy in this particular atom. Let's not worry about which atom or which particular electron state we're talking about. The key thing is that mathematical theory predicts that there is a probability of it being found here, a probability of it being found there, etc. And if we plot all of these probabilities out, then these clouds, these little graphics here, indicate the most likely place to be found is the densest or whitest part of the cloud. And as the cloud gets darker and darker and darker, then the electron is less and less and less likely to be found at that particular location. So maybe we ought to visualize the building blocks of matter in terms of these cloud thingies, these electron clouds. Well, even that doesn't necessarily tell the whole story. When we're dealing with atoms, we have a few choices. We could, if we wish, choose to describe atoms using words, and I've already used a lot of these. In fact, I've used all of these words already. We can talk about electrons as if they were particles. We can talk about waves. Atoms interact with light, and light is a wave, and electrons can sometimes behave like waves. We talked about electrons in a sense being analogous to planets in orbit around the sun. And also, electrons and other particles have a property called spin, which makes us think about the way the Earth is spinning on its axis. And I've already talked about the fact that different electrons in an atom might have different energies in much the same way that a planet at a different distance from the sun would have a different gravitational energy. So we have the choice, if we wish, to use English words to describe how an atom behaves. And we also have the option, if we wish, to use pictures, just like the splash screen that I showed at the start of the talk, which is sort of schematic of something or other which appears to be in weird and wonderful orbits around the nucleus, or we can think of it in terms of probability clouds, functions that tell us the probability of finding an electron at a particular location in space. Which should we be using if we're trying to understand the quantum world of what an atom is and how atoms produce molecules and ultimately how molecules produce us? Should we be using words or should we be using pictures? Which is the right way of doing it? Well, the simple answer, unfortunately, is neither. Neither words nor pictures will actually help us understand the way atoms behave. There is only one way of understanding atoms. And I'm sorry to say that that way is maths. That's why we teach students maths in a physics degree, because you have to. There is no choice whatsoever. There is no way you can explain the world in pictures or words. You have to use mathematics. The mathematics is rather more tricky than that little equation I've shown next door to the maths ellipse there. But ultimately, it would appear that the way that the world is built, the way atoms work, the behavior of all particles, including those particles that make atoms, including all atoms that make molecules, it would appear that the way everything behaves is based on the theory of quantum mechanics, which effectively is just a mathematical structure, which says, let us assume that electrons behave like this, that other particles behave like that. Then when we bring them together, we have a structure that defines the way an atom works. And we can, of course, try and link that to other things, because maths alone is of no use to us. If one scientist wants to talk to another scientist, okay, you can write down the maths, but ultimately you have to talk to each other. And so we start to use words to describe what we're talking about. And it might be useful to have some of the maths displayed as pictures. So in a sense, that bottom right picture of these electron clouds are effectively a pictorial representation of what the maths is telling us. But we have a problem when we start to use words, because words are confusing. No matter how well you try and define them, words are confusing, mainly because words are ambiguous. We wish to talk about the structure of atoms, says Heisenberg, but we cannot talk about atoms in ordinary language. And that is the problem we have. If we want to describe an atom, how do we describe an atom? Well, we sort of have to use the language that we've built up over a few, I don't know how many thousand years, a language which is designed for day-to-day living. A language that's designed to be able to warn your friend there's a lion over there about to eat you. A language that defines how you're going to get your next meal. That language is not really written to describe atoms, but unfortunately that language is the language we are now using to try and describe how atoms work. Heisenberg recognized back in the very early days of quantum mechanics, the maths works, but we shouldn't, in a sense, use ordinary language to describe atoms. If we use ordinary words, we should remember that those words don't carry the meaning that we think they carry. So would it be better to use words that don't have any baggage, don't have any preconceptions? Rather than saying electrons orbit the nucleus and electrons spin inside the atom, would it be better to say the slithy toes did gyre and gimble in the wave? That carries exactly the same amount of information as the previous sentence in red. The only reason you think the first one carries more information is because you think you know what's meant by orbit. You think of the Earth orbiting the sun, and you think you know what you mean by spin. You think of the Earth spinning on its axis. Those words have preconceptions, and those preconceptions color the way we think about the way those words describe atoms. But orbit and spin, for instance, do not mean what you think they mean, because atoms don't behave the same way as a solar system. And that's a bit of a problem. We should have used the second sentence in red, right at the start, rather than borrow other words which have a different meaning between the macroscopic world and the microscopic world. But it's too late. We've been using words like orbit and spin when referring to angular momentum of electrons in an atom. We've been using orbit and spin for nigh on 100 years, and it's too late to change. Everybody in the last 100 years has been learning quantum mechanics the same way, and those words carry a baggage with them, and we just have to learn to live with that. But that is precisely why teaching quantum mechanics is difficult. You're trying to teach students about the ideas of quantum mechanics, and you're using words that they think mean one thing, whereas in fact they mean something slightly different. And that is part of the problem. They have to learn the mathematics of what quantum mechanics is telling them about way atoms behave, and they have to throw away some of their preconceptions as to what they think the words mean. That's a double whammy in terms of the difficulty in understanding what quantum mechanics is telling us. Bohr. Everything we call real is made of things that cannot be regarded as real. That is an amazing statement. You and I think we know what we understand by reality. We pick up a cup and we tap it and we think we know exactly what we mean by a solid object. But when we drill down to what's actually going on at the quantum level, at the atomic level, then Bohr did not pretend that these were billiard balls zooming around other billiard balls. He didn't pretend it was a mini solar system. He basically treated as an atom as a mathematical concept, and in a sense, you cannot regard an atom as real. And yet everything around us that we would call real is made of atoms. And that is, again, part of the fundamental problem. So even one of the great architects of the so-called Bohr model of the atom had to recognize that there's a problem. We're building atoms out of these mathematical models, but can we regard these things as actually real? Schrödinger. Atomic physics has shown that atoms have no meaning, but can only be understood in experimental measurement. That's almost saying the same thing. Atoms themselves have no reality, they have no meaning, they're just a mathematical construct. The only thing that actually matters is that quantum mechanics can tell us that if you try and make a measurement, for instance, if you look at the light that's coming from this atom and you apply a magnetic field to that atom, how is the light going to change? Quantum mechanics can tell you what the answer will be. The mathematics says the light should do this if you take this atom and put it into this magnetic field. The only thing that matters is that when you measure the light, quantum mechanics tells you the right thing. It gives you the right answer. Schrödinger basically saying here that the actual building blocks themselves have no meaning. The only thing that has meaning is quantum mechanics, and atoms are just a mathematical construct, but quantum mechanics can tell you how things will behave if you make a measurement. So fundamental to the core of quantum mechanics is not the philosophy of how it's put together, it's can it tell you what will come out of a measurement if you make a measurement? That is absolutely central to quantum mechanics. I don't like it, and I'm sorry I ever had anything to do with it. This is the architect of quantum mechanics saying he's wrestling with what it actually means and how you interpret the maths of quantum mechanics in terms of the reality that we see around us. Quantum mechanics does not agree with common sense. This is the key problem. For instance, atoms, or indeed any particle you care to choose, are unpredictable. We can only talk about the probability of something happening. We can talk about the probability of a particle or an atom having a particular position in space, or a particular speed, or a particular energy. We can define lots of properties of atoms or molecules or cats and dogs or us or mountains. We can talk about these objects And we can talk about the probability that if we were to make a measurement of position, this is where we would likely get an answer. If we wanted to know the speed of this object, then the probability of getting this answer is this. We can't tell what the answer is going to be, but we can work out probabilities. Some people are not very comfortable with the idea that that's all we can ever say about reality. Atoms we think of as being small. They must be small because they make up everything. But strictly speaking, atoms don't have a size. From the previous statement in blue, we can only talk about probability. That means an electron that we think of as being, well, this is an electron in a hydrogen atom. Well, actually, that electron could be anywhere. There's a probability that it's close to the nucleus. That's actually quite a high probability. There's a lower probability that it's further from the nucleus. There's a very small probability that it's a micron distant. There's an even smaller probability that it's a meter away. There's a very small probability that the electron is actually in Australia. So we can't say that an atom actually is this big and the electron never strays more than this distance away from the nucleus. All we can talk about is the fact that it's getting less and less and less likely to be further and further and further away from the atom itself. So in that sense, all atoms overlap with all other atoms. You can't take an atom and isolate it completely from all other atoms because atoms don't have a finite size. And this is one that again foxes a lot of people. Atoms can be in two states at the same time. For instance, if we think about an electron, if we think about it like the Earth spinning on its axis, then electrons can spin clockwise and anti-clockwise at the same time. It's like saying the Earth rotates in a particular direction, but if the Earth behaved according to a quantum mechanical object, then the Earth could be rotating clockwise and anti-clockwise at the same time. That makes no sense whatsoever. It's a bit like tossing a coin, coming down on the back of your hand, and then saying, is it heads or tails? Well, common sense tells you it's one or the other. I don't know if it's heads, I don't know if it's tails, but obviously it's one or the other. No, the coin is heads and tails at the same time. And that is completely against common sense. And this is the third reason why trying to teach quantum mechanics to students is so difficult. Normally, you teach students and say, well, calculate this thing, calculate how many grains of sand there are in this bucket, calculate the mass of this thing, calculate the length of that thing, and you normally get an answer, and then you ask the student, does that make sense? Does that seem reasonable? You've just calculated the velocity of this ant running along the table, and you've got a velocity of 500 kilometers per second. Does that sound reasonable for an ant running along the table? Maybe you've made a mistake in your calculation. Most of the time, you ask an individual to do a calculation and then ask, does that make sense? However, in quantum mechanics, you cannot use your common sense to tell you that sounds right, that sounds wrong. Quantum mechanics comes up with too many things which go against common sense. Einstein said common sense is a collection of prejudices acquired by age 18. In other words, as a child, you ask questions about the world to try and understand how the world works. By the time you're an adult, you've got what everybody else would call common sense. You've got a certain world model of how you think the world works. The problem is, quantum mechanics often disagrees with common sense. And the bottom line is, as far as we can tell, whenever common sense disagrees with quantum mechanics is right and common sense is wrong. And that takes a lot of thinking about, and you have to throw away a lot of the ideas you've had, especially those ideas you've come up with over 18 years of childhood. When you start to learn about quantum mechanics, you've got to throw away some of the things that you thought were absolutely obvious common sense answers to particular problems. Einstein was never really happy with this idea of probability playing such an important role in quantum mechanics. The fact that you can't tell what is going to happen, you can only talk about the probability of something happening. This is even before you start talking about heads and tails at the same time. If you just imagine you can't calculate what a particular event is going to be, it's going to be one thing or another, you can only calculate the probabilities. Einstein was never really happy with this idea that fundamentally there is something about the universe which makes it probabilistic, not deterministic in the sense of once I know how it works, I can calculate the future indefinitely. God does not play dice, he famously said. God is subtle, but he is not malicious. And Einstein regarded a universe that was based on probability as being, in a sense, a malicious universe. If you can't predict the future, how are we going to make sense of the world around us? God does not play dice. Bohr didn't like this attitude. Bohr really did believe that probability was central to everything. So when Einstein said God does not play dice, Bohr got rather upset and said, stop telling God what to do. This is the way the universe is. Get over it. That is how it is. And people will continue to argue to this day as to whether quantum mechanics is right or wrong. But the bottom line is, quantum mechanics usually, in every instance we found up till now, gives the right answers. So why would we believe it's wrong? Let's have a look at three aspects of quantum mechanics. The fact that the order in which you do things matters, and I'll explain why that's important in just a second. Let's have a brief look at Schrödinger's cat, and then we'll finish with looking at atoms using quantum mechanics itself. So order matters. Now, I'm sure you know that in algebra, A times B is the same as B times A. 2 times 3 is exactly the same as 3 times 2. The answer is 6, and it makes no difference which order you put the numbers. It doesn't matter whether you multiply the first number by the second or the second number by the first. It makes no difference at all. However, in the mathematics of quantum mechanics, A times B is not the same as B times A. They are not equal to each other. What this means in quantum mechanics, I've said so what at the end, the A and the B are not necessarily just numbers. In quantum mechanics, A and B represent something we can measure. We want to measure some property A, and we want to measure some property B. For instance, a snooker ball is rolling across a table, and we want to know the position of the snooker ball, and we want to know how fast the snooker ball is moving. We want to know its position, and we want to know its speed or its velocity. Now, in quantum mechanics, the fact that A times B is not equal to B times A, that means if we measure its position and then measure its speed, we don't get the same answer as if we measure its speed and then measure its position. Even if they occur right after each other, a nanosecond later, we measure one, and then a nanosecond later, we measure the other. Measurement of one quantity can affect our previous knowledge of the other quantity. In Newtonian mechanics, if we wanted to know the position and the speed of the ball, then it wouldn't make any difference in principle if we measured the position and then worked out measured the velocity, or whether we measured the velocity and then measured the position. Measurement of one doesn't interfere with your previous knowledge of the other, but in quantum mechanics, it can. And the easiest way of demonstrating how weird that is to do a little thought experiment and ask ourselves, well, if things behaved the way that quantum mechanics says they behave, but if we scaled that up to an everyday example on a macroscopic scale of meters rather than a nanometer scale, what would be the consequence if the world behaved the way that quantum mechanics tells us? What if order mattered? Well, let's imagine we have a zoo with 4 animals in it. Not a very interesting zoo, perhaps, but let's just imagine that we've got a couple of carnivores and a couple of vegetarians. So what we have here is 2 carnivores, a lion, you can tell it's a carnivore from the teeth and the blood around its jaws, okay? And then we have a vulture on the right-hand side. So 2 quite definite carnivores. The bottom pair are vegetarians. On the bottom left, we have a water buck that's grazing quite happily. And on the bottom right, we have an ostrich. Okay, 2 carnivores, 2 vegetarians. But also we can think of them in a slightly different way. We can say that the left pair of animals, the lion and the water buck, both have 4 legs. And we can say that the 2 animals on the right both have wings. Okay, one flies and one doesn't, but forget that. They both have wings. So let's think about what happens if we do an experiment that behaves according to the rules of quantum mechanics. We're going to pick 2 of those animals out of the 4. Let's say, for example, let's pick the 2 vegetarian animals. So we've picked the waterbuck and the ostrich. We're now going to pick again and say, I'm now going to make a second selection, and I'm now going to choose what? I'm going to pick again, and I'm going to choose, let's say, the 4-legged animals. So what you would expect to get, having chosen the vegetarians, and now I'm going to choose the 4-legged animals, I would expect to get a waterbuck. But according to the rules of quantum mechanics, what I actually get is a waterbuck and a lion. In other words, somehow selecting the 4-legged animals has somehow made me completely forget the fact that I had originally just chosen the vegetarians. Magically, the carnivore is back again, because my choice of 4-legged animals has made me forget that I actually selected vegetarians. And that means that if I make a different order, if I now again select from those animals, but now I'm going to pick the 4-legged animals first. So now I'm going to pick the lion and the waterbuck. And now my second choice from those is going to be, from that pair, I'm going to pick the vegetarians. I now choose the vegetarians from that pair. I would expect to get the waterbuck, but what I actually find is a waterbuck and an ostrich. In other words, my choice of vegetarians has somehow made me forget the fact that my first choice was actually picking out the 4-legged animals. Doesn't make sense in terms of common sense, but that is how quantum mechanics works. Sometimes when you make a measurement of one thing, you scramble any knowledge you thought you had of another thing. Sometimes it scrambles, sometimes it doesn't. There are rules that tell you when this happens and when this doesn't happen. And it's rather important for our understanding of the quantum world. I'm not going to go into the details of the maths of how we come to that conclusion, but that is an example of how order matters. It makes no sense when you think about selecting animals or selecting socks from a sock drawer. If I want the long socks or the black socks, does it matter if I pick the long ones first and then take the black ones out? Or does it matter if I take the black ones out first and then separate the short ones from the long ones? Absolutely it matters if we're talking about a quantum mechanical world. Completely and utterly against our ideas of common sense. Schrödinger's cat is one of these examples where Schrödinger tried to bring home the fact that this is so far removed from common sense. I believe some students actually thought that Schrödinger did this experiment by taking a cat and putting it in a box, but no, this is purely a thought experiment. What if you were to take Schrödinger himself? What if you take a cat who's looking a little bit nervous, put him in a box and seal the box, and then you have something like maybe a radioactive particle decaying with a probability of 50-50 it will decay or won't decay. And on the basis of whether or not it decays, then a robot takes a hammer, smashes this vial of poison, and then kills the cat. If the radioactive particle does decay, the cat ends up as dead. If the radioactive particle doesn't decay, then the cat is alive. But according to the rules of quantum mechanics, that atom is in 2 states at the same time. It has decayed and it hasn't decayed. These both exist at the same time, just like an electron we can think of as spinning one way and spinning the other way at the same time. Or a coin can be heads and tails at the same time. So if quantum mechanically that's how we describe the atom, that means that the cat must be dead and alive at the same time. If the trigger, if you like, is yes and no, then the cat must be dead and not dead. And the point is, it's not simply that we don't know which it is. It's not simply that, like the coin on the hand, it's one or the other, but we don't know yet until we open the box. No, that is not what quantum mechanics says. It doesn't say the cat is alive or the cat is dead, and you will find out the answer when you open the box. Quantum mechanics says that the cat is both. The cat is both dead and alive at the same time. And when you open the box, you effectively make a measurement on the cat and find out what it is. And at that instant, the cat becomes either 100% dead or 100% alive. But whilst the box is closed, the cat is in both states at the same time. That is the conclusion that Schrödinger came to, and because, again, that is completely contrary to common sense, that's why Schrödinger came up with this idea of an experiment, a thought experiment, not a real experiment, in which he showed the absurdity of what's going on. But you can trace the absurdity from quantum mechanics, which appears to be correct, all the way to a cat. And at no point do you say, well, something has gone wrong. We stopped using quantum mechanics here, and then cats are a completely different thing to atoms. If atoms behave that way, then that would imply that cats must behave that way as well. So how do we know that quantum mechanics is right? If it keeps giving us answers that are contrary to common sense, why do we keep using quantum mechanics? Well, the bottom line is nothing has proved it wrong. That's not the same that it's been saying that it's been proved right. For 100 years or so, we've tested quantum mechanics in various guises. And in the millions of ways that the tests have been done up till now, quantum mechanics always seems to be correct. You can't prove a theory is correct. You can only disprove a theory by making the prediction and then showing the prediction is wrong. So far, quantum mechanics has made lots of predictions, and every prediction is correct. The calculation we do, the measurement we do, always agrees with the fundamental theory of quantum mechanics. So that doesn't prove that quantum mechanics is right, but we have no reason whatsoever to disbelieve it. It predicts results that are impossible by classical mechanics. So Newton says things should behave this way. We've made lots of observations of objects in which quantum mechanics makes a prediction which is right, and classical mechanics, Newtonian mechanics, makes a prediction which is wrong. So we know in that sense, quantum mechanics is better than Newtonian mechanics when we're applying it to lots of relatively small objects. If we're talking about the Earth going round the sun, well, it looks like Newtonian mechanics works pretty well. But if we're talking about atoms and molecules and small objects, then quantum mechanics appears to be correct and classical mechanics appears to be wrong. And we can actually use quantum theory, we can use quantum mechanics to actually not just philosophize about the way the world should be, we can actually build microscopes that can see atoms. And we do that using what is called a scanning tunneling microscope, or an STM for short. What we do is take a sharp tip of material, and here I've shown the atoms way too big just to give you an idea. So we can imagine a sort of pyramid, an upside down pyramid made of lots of atoms, and we can assume that our sample is a slab of metal of some kind. And again, I'm showing the atoms as far larger than they actually are. And we're going to separate the two by a certain distance. And we can apply a voltage between them and measure how much current flows. And we would expect that no current flows as long as there's a gap, because there's no circuit and we can't conduct electricity. But quantum mechanics says that, well, actually, electrons from one object, the tip, for instance, can magically almost find its way into the sample, even though it's arguably never been anywhere in the gap between. In other words, there's a probability that the electrons exist in the tip, and we can calculate what that is from quantum mechanics. But quantum mechanics says that if we think about this atom at the very tip there, there's a probability that the electron in that region actually is no longer in that region. There's a probability that that electron has found its way to the sample. We don't have to ask the question, how did it get there? Quantum mechanics tells us the probability the electron is here and the probability the electron is there. And there's a finite probability that a current flows even when there's a gap between these two objects, the tip and the sample. And we can make a microscope out of that by taking the tip and moving it across the sample. Whoops, we find that the amount of current that flows is very sensitive to just how far it is from the tip to the sample, this measurement here that I call D. You can see that if we change that D by one atom, you would think that, well, if it's one atom closer, surely that's not going to make much difference as to how much current flows. Actually, the current can change by a factor of 10 or a factor of 100. it can change by an enormous amount, even though you've only changed the distance from the tip to the sample by a fraction of an atom's diameter, thinking of an atom in the conventional way as being something which is sort of smaller than nanometer, even though we've agreed that electrons can exist according to probability some distance away. So by moving the tip across the sample and measuring the current at each point, we can actually map out not just the fact that atoms are in particular places, we can even see that the surface of a material is corrugated because it's made of individual atoms. It's not dead flat, even though the number of atoms is completely the same everywhere. We can still see the corrugation because there's an atom here and no atom there, and an atom here and no atom there. So when we actually measure the current as a function of where the tip is, we find that if we build ourselves an STM, there's a handsome scientist standing in front of an STM. The STM, the scanning tunneling microscope, is inside this vacuum vessel to try and keep air away. We're bringing a sharp tip close to a surface, and we want to get them fairly close to each other. We don't want air molecules, we don't want oxygen and nitrogen and other stuff getting in the way. So we put it inside a vacuum vessel. We take the air out, and you can see there the pressure inside is about 10 to the minus 13 atmospheres, so a very good vacuum inside. And then we can obtain images such as this, obtained by a colleague from the University of Manchester. You see the scale in the bottom left-hand corner there? That scale bar is 2 nanometers. So we see individual bumps, individual mountains on the surface on a spatial scale much less than 1 nanometer. And we can interpret that as being, we are looking at atoms. In this particular case, the atoms, you can notice, are not uniformly spread over the surface. This happens to be a surface of iron oxide. It's a mixture of different phases, Fe2O3, Fe3O4. But the point is that the atoms are not uniformly spread over the surface. They bunch together in little islands of one phase, separated by a different phase of iron. Surface science is all about looking at atoms and molecules and seeing how they behave on the surface, not inside the bulk of a material, but how do they behave when they're at the interface between a solid material and either a liquid or a gas or possibly a vacuum. So that tells you that scanning tunneling microscopy does actually work, and it's based fundamentally on the fact that the electron can go from the tip to the sample without actually traveling between the two. It's a quantum mechanical phenomena, and that phenomena is called tunneling, which is why this is called the scanning tunneling microscope. There are other examples of manifesting tunneling, which I won't go into, but for instance, radioactivity is a manifestation of quantum tunneling as well. When we look at the world on the scale of atoms, using, for instance, a scanning tunneling microscope, we see interesting patterns. Here's a picture taken on a scale of 10 nanometers. That's the length of the image itself. And we can see particular patterns, as well as what looks like patterns of 10 atoms in a sort of daisy there. We also see a pattern of 5 atoms in a pentagon. And that, not surprisingly, explains why we get crystals on a macroscopic scale of millimeters that mirror this same idea. On the spatial scale of millimeters, it's reflecting the same ordering of the building blocks, the atoms in this particular case. This happens to be an alloy. Let's not worry about which particular alloy. The atoms in this alloy have arranged themselves in pentagons, and that is one of the reasons that we find that this particular metal crystallizes into this dodecahedron structure that we see on the macroscopic scale. It's interesting to note that we need quantum mechanics to explain exactly what these structures are, but still we see patterns that are not in themselves quantum mechanical. When we start to measure, for instance, the distance between atoms that we can see as these bright blobs in this image, if we look at the ratio of this distance to that distance for particular sets of atoms, we find that certain ratios are adopted in this particular alloy, and the ratio turns out to be this particular number, 1.618. Why is that interesting? Why is it interesting that quantum mechanically the structure of atoms at the quantum scale gives us a particular ratio between the distances between atoms? Well, because that number crops up on a macroscopic scale as well. It crops up when you start counting the scales on a pineapple. You can go one way, indicated by the purple arrow, and count how many scales there are on a pineapple. You can go in the other direction, indicated by the cyan arrow, and count how many scales you have. Take the ratio of those two numbers, you get 1.6 and a bit. You can see the same when you look at the patterns in the spirals of a seed head, such as a sunflower. You can count how many seeds are there. If you follow one of these spiral arms in the clockwise sense, you get a number. And if you follow the spiral in the anti-clockwise sense, you get a different number. Take the ratios of those two numbers, it comes out to be 1.62-ish. So for some reason, nature has decided that patterns exist not only on the macroscopic scale, but sometimes those patterns are also imprinted on the quantum scale. So we do see things on the quantum scale that are not necessarily intrinsically quantum mechanical in origin. So when we look at what's going on with individual atoms, we have to ask ourselves, what is it that's actually producing that particular structure, that particular pattern, which then leads to this macroscopic structure and these macroscopic properties of this alloy or this metal or this semiconductor or whatever it is we're looking at. This is a quite remarkable image. It's a false color image, but we don't have to worry about that. It's an image showing that we've placed a whole load of atoms in a circle, in a corral, and atoms can indeed be moved. They are not only possible to image them with a scanning tunneling microscope, it's possible to use that same microscope to actually push the atoms around, and actually, in this case, after a fair bit of time, push the atoms so that they make a circle. So we can see what appear to be individual atoms that appear to behave like particles because they seem to have a particular position on the surface. But what's going on inside this corral? Well, it looks like ripples in a pond. If you had a teacup and you drop something into the middle of the surface of the tea, you would get ripples coming out like ripples on a pond. And it looks like that's what we're seeing there. This one image seems to be capturing the fact that some atoms appear to be behaving like particles, the ones in the corral, but what's inside the corral seems to be behaving like waves. Again, this is an example that one entity, you can't necessarily say this is a particle, this is a wave. It is quite common to find that a lot of systems have wave-like and particle-like properties, sometimes at the same time, which is rather bizarre. Final word goes to Bohr, the penultimate word goes to Bohr. If quantum mechanics hasn't profoundly shocked you, then you haven't understood it. Great quote. That's been requoted various times, and Richard Feynman has said, I think I can safely say that no one understands quantum mechanics. It is not uncommon to tell our students, if you think you understand quantum mechanics, then you haven't understood quantum mechanics. Everybody has to be, what's the word? Everybody has to realize that no one really understands what's going on. We can learn the maths, we can apply the maths, we can make predictions of the probability that this is going to happen and that's going to happen. But ultimately, we are still shocked by it. There is another great phrase, shut up and calculate. Yes, quantum mechanics is confusing. Yes, quantum mechanics goes against common sense. But just use it as a tool. It is, in a sense, a set of tools. It is a mechanics. It's a theory. It's a self-contained theory which makes predictions. So just treat it as a, this is the correct model. Let's see what it predicts. The fact that it goes against common sense, well, just park that for a minute, because it doesn't actually matter that it goes against common sense, because it gets the right results anyway. So yes, if you stop and think about it, quantum mechanics is bizarre and shocking. But after dealing with quantum mechanics for enough decades, you start to get over it and say, well, yes, it is bizarre, it is shocking, but I'll park that and I'll just get on and use it, because ultimately it's a really useful set of tools. Some people are worrying about the philosophical aspects. Some people don't worry about the philosophical aspects. They just get on and use it. One of my favorite quotes is from Einstein. The most incomprehensible thing about the world is that it is comprehensible. It might be that we couldn't make any sense whatsoever of what's going on at the atomic level. It might be that the universe was so complex we would never have a chance of understanding cosmology, the origin of the universe, the Big Bang, the existence that we know around us. But for some reason or another, the world, the universe, is comprehensible. It is a limitation of our brain that makes life difficult, whether we're trying to understand warped space and the origin of the universe, or whether we're trying to understand atoms on a tiny scale. Whatever's going on, the most amazing thing is that we do stand a chance of understanding what's going on. Is it possible that you could not draw on the screen for the time being? Thank you. So I think that's a great quote, because there is no reason why the universe has to be comprehensible. There is no reason why it should be possible to understand quantum mechanics. It is quite reasonable that we understand the world around us on the scale that we're dealing with, but there's no particular reason why the universe should be built in such a way that we understand how atoms work. So the fact that we can get an understanding of how atoms work is in itself amazing. I'd like to finish with this image. You can see from the scale here, this is 850 picometers in size. So that's less than 1 nanometer on the edge of the square, less than 1/1000th of a meter. And here we can see a few individual atoms. I believe these are carbon atoms that we're looking at. If that was expanded out on that particular scale, a grain of sand would be about the size of the moon, roughly speaking, a few thousand miles across. And whenever you look at an STM image of individual atoms, it's very tempting not to think of William Blake and thinking about to see a world in a grain of sand when you realize the scales that you're looking at. To see a world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Thank you all very much.